Okay, so now the recording has started, and today, this lab period, we're going to be discussing the week 3, day 1, Diels Alder reaction. So here we go. And then, of course, review the video. The pre-lab notebook we already covered today. The pre-lab quiz, if you hadn't already completed it, please make sure that that is done. It is due before the class period, but of course I understand if people possibly forget to complete it, so please ASAP if you have not. And then we'll review the data and we'll also address that once we get there. And we will briefly view a couple things on the video once we are over with the lab manual discussion. So let me switch over here and open the PDF. Okay, now all right, now sharing the PDF. All right, so the Diels Alder reaction itself is considered a type of reaction called a cycloaddition. And the reaction involves 3 pi bonds, and that would be 2 from the diene and 1 from the dienophile, in one reaction in order to form a 6-membered ring. So we would know some things such as cyclohexane, benzene, etc. These are multiple types of rings. And when we talk about cycloadditions, we talk about them numerically. So a total of 4 pi electrons are involved in this. And so we would call this a 4-2 cycloaddition. As my undergraduate, I was a little bit confused on what they meant by that. What they mean here is the electrons. So right here on the diene, this is the first part. 1, 2, there's 2 double bonds. That means that there are 4 pi electrons involved on the diene. The dienophile, this should actually be placed here because this alkene is the dienophile, and it is 2 electrons from the 2 pi electrons. So that would be 4 plus 2 cycloaddition. And a good rule of thumb is to label them with numbers so that way that you can address the shifting of the pi electrons as it goes. So the mechanism for it is a 4 plus 2 mechanism. It occurs all at once. What happens is that it actually shifts over. The electrons shift from the 1-2 alkene right here over to the 2-3. And then the 3-4 shifts over to create a single bond over to 4-5, or a sigma bond in this case. And then the 5-6 pi electrons, they actually shift over to create a new sigma bond to the 1-6. So we actually break 2 pi bonds in order to create 2 sigma bonds here between 4-5, 1 and 6. And then we additionally also undergo the pi electron shift over to 2-3. So any forms of these sorts of Diels Alder reactions will involve primarily the diene and the dienophile. And then this is the intermediate reaction that we can see as the mechanism scheme. And then some other things to note that normal Diels Alder reactions are favored by electron donating groups on the diene, and then electron withdrawing groups on the dienophile. And in this case, that's not really a primary example. This is just the most simple explanation of a 4-2 cycloaddition here. So when they speak of it, the diene must be capable of achieving an S-cis conformation to generate the cis double bond in the cyclohexane product. And they're talking about here for the 2-3 cis diene. So going forward down here, we should go forward to talk about the formation of a bridged heterocycle. And in this case, it is this long one here, but it is 9,10 dihydro anthracene 9,10 alpha beta succinic anhydride. And I know that's a mouthful, but if you look at at it, it's not too bad. So the maleic anhydride becomes a succinic anhydride on here, which is bridged over onto the anthracene base. So when you think about it, think about the anthracene base as the bottom part of it, and then attached on top of it is going to be the alpha beta succinic anhydride. And then the numbering here is the positions of where this is actually bound onto the anthracene as a base molecule. And so, just overall, this is just parts of nomenclature. They have a separate system of nomenclature. Additionally, there's also forms of nomenclature with regards to bridged heterocycles that involves brackets that you've probably seen before, but it doesn't show here. However, the main thing here is that anthracene acts as the diene, and maleic anhydride functions as the dienophile. So, as they said above, that electron withdrawing groups on the dienophile, in this case the maleic anhydride, we can see we have some electron withdrawing groups because the oxygens want to pull away electrons from the alkene here. And then anthracene is just a decent situation. It has a few electron donating groups from the benzene ring, allowing it to resonate back and forth. You probably remember from lower levels of chemistry, OChem 1, etc. And then, so we primarily use xylene here. Xylene is really good in lab for very high temperatures because with these sorts of reactions, you really have to, overcome a very high barrier of energy. And so in order to do that, we normally in chemistry want to utilize one of two things. That would be a catalyst or temperature. So with this case, xylene or dimethylbenzene can be used in order to perform a very high temperature reaction and allow it to create our bridged heterocycle system. So another point here is melting temperature analysis will be used to characterize the product. So I'm not sure actually if I saw that on some people's papers. So listen carefully here. The melting point apparatus, or the melting point machine will be one of the instruments you need to have. A heating mantle or heating plate, stir plate will be counted additionally as one of the machines. And then let's go through here briefly, since this is also kind of a shorter. A lot of these, unfortunately, are very heavy in lab experiments, and I wish that you could experience them, but at least we can kind of walk through the video, because this reaction itself is mechanistically, it's a little difficult. It's kind of hard to understand heterocyclic systems. And then, but in lab, it's not that hard. It's honestly very simple. You put the stuff together, got to make sure it's dry, heat it up, and you just run it, and then you're good to go. So firstly, the steps would be to synthesize it, of course, then you isolate, and then you measure the melting temperature of the product. So you place all of them in here into the reaction flask, then you record everything, add in your solvent, xylene, so it's flammable, no Bunsen burners. I don't want to see that on any person's thing. Always heating mantle or sort of a heating bath, any sort of heating situation you want to place there. Then you set up a reflux with a condenser. Make sure to have your condenser added into your apparatus section. Then, of course, greasing the joints. We know this as a common situation. Then here they say to utilize a sand bath. You can put sand bath, you can put heating mantle, you can put any sort of thing as a machine. So it is a machine producing heat for the reaction and would be considered a machine. So melting point machine, sand bath or heating mantle machine. Then we reflux it at extreme temperatures, almost 200 degrees Celsius here, for 30 minutes. Then on the sideline, we're going to have the ice water bath in a 250 milliliter beaker, and you would obtain 3 milliliters of xylene, and then you would place it in there to cool down. Then after 30 minutes, then you would turn off your heat, turn your sand bath off, let it cool, because it's going to be extremely hot glassware. Like as they say here, wait at least 15 minutes. You have to wait because you don't want the glass to crack if you accidentally placed it in while it was scalding hot into the ice water. That could cause the glass to shatter. We don't want to do that. So we were to wait till it's room temperature glass. We're good to go. Then take the flask over into the ice water bath and let it sit there to cool down. That's when we'll see the crystallization. So actually this heterocyclic structure can actually crystallize out of the xylene solvent, because it's kind of like in your previous labs, you probably had a recrystallization where you saw that something can dissolve at very high temperatures. But whenever we come down and we lower the temperature, the solubility simultaneously lowers, and especially in a heterocyclic system with the ketones and your hydroxyl group on there, then that's going to actually be a little bit more polar, meaning it's going to want to pull out of xylene because xylene is a very nonpolar solvent. So we're going to pull it over there. You're going to collect the crystals using vacuum filtration. So of course, have your Buchner funnel listed in there, and then all of the glassware that you need to know if you need to set up a vacuum filtration system. Then you'll put your filter paper on there. You would pour your solution over there, and then you would wash and dry the crystals with a cold xylene. So that side test tube you have, that's used to wash it. And we use cold xylene because of that principle I was speaking of with regards to recrystallization, that we want to make sure we only pull out any impurities that are soluble in cold xylene, and we leave our nice crystals on the filter paper. So then we place it over onto the watch glass to dry. Then we finally will weigh our product and make sure this last part here, if we're going to do the melting point experiment, then we need to also have the melting point machine. And finally, so don't forget, the data analysis here will be part of your post-lab questions, so you can have it all together if you want to, whichever way that you format, I don't mind. Just make sure to utilize the data that we have provided, and we'll take a look at that here afterwards. And additionally, to complete all of the post-lab questions down here. So let me jump over, and then we can just take a quick peek over at the video that we have provided by Dr. Rastogi. And then finally, we will look at everyone's data and discuss if we need to have anyone's, if everyone has their data, because I did get a couple emails regarding people being worried about not having data. So let me pull up this YouTube video really quick. Okay, and so we're going to be skipping through most of it because I would like you to review it yourself in full, but I do want to primarily have the system set up here. Okay, yeah, so this actually is a good part for me to show you as well, is that if we wanted to actually go forward and create a different part, then we would have to actually perform a different version of the Diels Alder, where we would either increase the heat even more or utilizing a catalyst to do it on the left benzene ring. But in this case, the activation energy is much lower for performing this Diels Alder reaction in the center. So we would actually only perform this here in order to create what we want. So this is just kind of a showing the activation energy requirement for a reaction to occur. And we can utilize that going forward into labs with different sorts of catalysts and such. So in your section of the hazards, remember, we need to add every chemical we're utilizing. So anthracene, this is organic, and alone maleic anhydride would be considered aqueous or organic. I'm not too picky on that one. Just make sure in your hazards that you have all of them listed. Xylene is organic. There is no question about it. It is purely organic solvent. And then, of course, you need to be dressed appropriately in lab attire because it can be dangerous with extreme heat. He placed the boiling stones in there. And then, of course, we just add our stuff in. Like I said, it's very, very straightforward. You put everything into your reaction flask, and then you get going. So here we have our condenser. And the condenser is utilized so that way we can reflux. So what happens is when the xylene starts to boil up, the water goes through the condenser and cools that xylene back down, condensing it, allowing it to go back down into our round bottom flask. And so going forward, going to keep moving forward here. And then here they have the thermometer that goes down in just to make sure we have the correct temperature happening there. And it's within the xylene itself to make sure that we have the correct temperature at the still pot, which would be different if we were performing a distillation. And then after 30 minutes, we're going to go ahead and remove this. And as you see, it's so hot, it's still refluxing without even having the heating mantle on there. And that is why we need to make sure to allow it to cool to room temperature. And then, of course, we have our xylene test tube over here cooling with the solution, just the xylene in there. So that way we can utilize it going forward for our filtration and purification. So they're letting it sit. Now they've taken it over here, they placed it into the ice, and you see the glass didn't crack because they let it cool to room temperature. And then now you can see it's becoming more cloudy, so it's falling out of solution here. And so Going forward, okay, so now we have our filtration set up. So remember, have your hose, have your flask with the adapter on it, have your Buchner funnel, have your filter paper. All of that should be apparatuses. None of this is a machine. Then we're going to go ahead and pour over everything. So you see, we want to swiftly just pour it over to get everything over into the filter paper. And going through is going to be the silane and crude product. And you can already see here, some of it's a little bit too bright here, but some of the crude product is already in there and just sitting on top. It's ready. Now we pour the xylene over, the cold xylene over from our test tube into the round bottom flask, shake it around a little bit, and then we pull over the rest of the stuff that may be left in the round bottom and then pour it over into there. And additionally, if you were in lab, you needed to get a little bit more out, you have a little bit left, take more cold xylene, pour it into your round bottom, and then you pour it back over into there. So that's basically what I wanted to show you because it's a very straightforward reaction, and you can see the crude products just sitting up there. And then let me see if there's a part here. Yeah, so see, there's a nice example of it's kind of like crystally. You can see it's a little shiny. It's a nice product. And then going forward, you're going to flip it over. And then, oh yeah, you want to add in an oven here as well. So please add the oven in the machines. So that way that we can dry it off, get all the xylene out of there, and be left with our nice product. Then we weigh it. Of course, I know everyone knows how to use a scale because we've had a handful of labs. Then we stuff the tube, that glass rod, with our with our sample, our final pure sample, and then we place it into another glass tube that lets it fall down and actually be packed down into the melting point capillary tube. Okay, so that does it a couple times, so that way so you can see now everything's at the bottom. Whenever you do it, it shoves it down to the bottom. So here's our melting station. So you want your melting point machine. Some melting point machines already have their thermometer, everything. You don't have to put the LabQuest on there, but if you do put the LabQuest, that's cool too. It depends which lab we were working in. Some of them have the older labs where you just have the thermometer and melting point machine and that's it. This one, in this case, has the LabQuest. I'm not picky on which one that you want to place, but as you see, we put the camera in there and you can kind of see that it's just sitting there. We're just waiting. And then, like, of course, melting point is just a waiting game and you just continue to go until it finally becomes a liquid. And I'm not sure if I don't think they actually zoomed in to show the liquid. But here is a good point to review because they're going to go through all the stuff of what you need to be utilizing within your data analysis section. So I greatly recommend to watch the full video through, take a couple of notes if you need to, and then finally we can come over to discuss the data and close up our section. So let me open this module back open. Okay, so when I click the data at the bottom of our module, we have all the people here. So what I need you to do is go forward and review this, look over here, let me know if you're not here, and then we're gonna make the changes here together today. So that way you don't have to email me down the week and then let me know that you need to do it. So right now, go ahead and open up your module, check it, and in chat, let me know if I need to add you on there. And then finally, before I close this out just for the video, and then we'll go into the discussion together, is that the HOLA Chemex, I don't currently see anybody posting down here yet. So please go forward to complete the discussion portion and then review the videos here that he has provided. So that way that everyone can go forward to be preparing for the poster, and as well, the discussion needs to be completed very soon, so that way Dr. Osogin can stop, reminding me to remind y'all. Okay, so that'll be it for the video here. I'm going to end the video out, and then we'll go forward into the Q&A portion. Thanks for watching the video, and have a great day.